mixture of AI and traditional systems, or all AI, we need to be able to actually do testing of the neural networks. So I'm going to look at how we would test the deep neural networks part of the systems.
네, 그래서 이제 실제적으로 테스트, 뉴럴 네트워크 신경망을 어떻게 테스트하는지를 살펴볼 예정입니다.
And our first problem is that these systems are typically going to be very complex. Obviously there will be some that are really small, which are part maybe of the Internet of Things, but many of them will be complex. And these complex systems, if we're trying to teach them to mimic human behaviour, which we need to do it, for instance, an autonomous car needs to copy what humans do on the road, otherwise humans will not be able to drive beside the autonomous cars. We want their behaviour to be the same as us. The trouble is, if we want the behaviour to be the same as us, when we're testing, then the oracle for the testing is it has to be like a human. Now, a lot of the time, we find it very difficult to describe how we make decisions. How do we recognise something? How do we decide to turn that way instead of that way when there's something in the road? It happens so quickly that for us it's second nature. It isn't a systematic process. And actually describing that and therefore being able to test against that is going to be really difficult.
네, 그래서 가장 큰 문제점 중에 하나는 대부분의 이런 자율 시스템이 굉장히 복잡하다는 거하고, 그리고 이런 시스템은 사람의 행동을 이렇게 뭐 카피하기 위해서 만들어지는데, 실제 사람이 어떤 행동을 하는지, 어떤 결정을 왜 내리는지를 설명하기도 굉장히 어렵고, 그렇기 때문에 이런 시스템들한테 그렇게 하도록 하는 게 굉장히 어렵습니다.
As we saw in the previous section, these systems are probabilistic and non-deterministic, and therefore they make our testing much more difficult, and we'll have to probably do we will have to execute many more test cases. Hopefully we'll be able to run those test cases very quickly, as we'll talk about a bit later.
네, 그래서 앞에서 설명드린 바와 같이 이런 시스템들은 결정론적이지 않고 확률적이기 때문에 굉장히 많은 수의 테스트를 수행해야 되고, 뭐 실제적으로 희망사항이라고 한다면 그런 테스트를 굉장히 빨리 수행하기를 희망합니다.
And a third problem with these systems is that they are really complex. At the end of last year, at the biggest AI conference in the world, the Google AI scientist doing the keynote described how these systems were built as alchemy. Now, alchemy in English is turning metal into gold. It's not science, it's impossible. Other people described it as a craft, unscientific, a field full of mysteries, hit and miss. Now, some people argued against this and said, no, we know how to build them perfectly. But actually, when you look at the systems and you get people to explain, why did you choose this model? Why have you made this parameter selection? Why have you added this extra coding? They can't explain. It's not scientific. So until the experts in the field believe it's scientific, it's going to make the testing really difficult, because we can't trust that there's good engineering underneath that we're testing.
네, 그래서 실제적으로 이런 모델하고 파라미터 셀렉션을 설명하라고 했을 때, 뭐 어떤 사람은 영문술이라고 하기도 하고, 어떤 사람은 뭐 예술이지 과학이 아니라고 설명하는 사람들도 있기 때문에, 실제적으로 이게 하나의 사이언스가 되기 전까지는 이런 시스템의 기본적인 바탕이 되는 게 뭔지 모르고 그런 것들을 테스트하기가 굉장히 어렵다는 말씀을 해주셨습니다.
So we have systems which are non-linear, they're complex, and when everyone says things are complex, So to just give you an example, if you remember at the beginning I mentioned that there was a very simple autonomous car system that NVIDIA had produced after 72 hours of training. 72 hours, 3 days of training. 3 days of training, that system has 27 million connections and 250,000 parameters. So after 3 days, really complex system.
네, 그래서 앞에서 들어드렸던 예제와 같이 엔비디아에서 72시간 만에 구성한 시스템도 결국 까봤더니 뭐 2,700만 개의 커넥션과 250만 개의 25만 개의 파라미터를 가지고 있는 그런 복잡한 시스템이었습니다.
And recently, they've discovered a special type of defect just for machine learning systems. This is called an adversarial defect. People aren't clear what causes this defect, and they are absolutely not clear how to detect the code that creates it. But they know it exists because they can see it happening. Now, I don't have the knowledge to explain, and I'm not sure many people actually know how it's created. But I can explain the effect. So imagine we have a deep neural network, we have some inputs, it transforms those inputs, as any system does, into outputs. Now, typically you would expect there to be some simple mapping, or maybe more complex mapping, but an obvious mapping between the inputs and the outputs, like I've shown you here. What happens with adversarial defects is that all of a sudden, one slight change in the inputs causes an enormous change to the outputs. Now, in a safety-related system, this is a real problem, because if we can't predict this, our car might be getting input to tell it to go this way, then all of a sudden it gets told to go that way. So it could be a real problem from a safety perspective.
네, 최근에 나타나는 결함 유형 중에 하나가 저는 적대적인 결함인데, 쟤네들은 특정한 인풋이 주어졌을 때 특정한 아웃풋, 비슷한 그런 트렌드를 가지는 아웃풋을 기대하는 상황에서 전혀 엉뚱한, 지금 표에서 보시는 저런 결과가 나오게 되고, 저런 결과는 이제 뭐 안전 치명적인 시스템에서는 예측할 수 없기 때문에 굉장히 큰 문제를 야기하게 됩니다.
I work better at understanding examples. So here's an example of one of these adversarial perturbations, and we've got 12 pictures of a cat here, and I expect they all look very similar to you. They're all different. Every picture is different. So I've gone into every one of these pictures and changed it so that there are some different pixels. Now, as far as a human is concerned, if we were trying to classify these, they're all cats. If there's an adversarial defect, what happens is some tiny change, which might only be a few bits, a few pixels, causes the machine learning system, our neural network, to label this one a dog. Now, as far as the humans are concerned, it's really obvious. They're all cats. But as far as the neural network's concerned, that tiny change gives a completely different result, which generates a whole new class of testing that we need to do to take out these bugs, if we know how to take them out. Because no one's really clear that we can take out these bugs. In which case, we have to write software that copes with the bugs, that is fault tolerant.
네, 그래서 보시는 사진들은 뭐 사람 눈에는 당연히 다 고양이처럼 보이는데 실제적으로 각 사진마다 몇 개의 픽셀이 다르고요. 그 중에서 어떤 픽셀을 건드렸을 때 가상망한테는 이제 고양이가 아니라 강아지로 인식하게 만드는 그런 적대적인 그런 오류가 생기게 됩니다. 근데 이런 오류들을 어떻게 발견할 수 있는지는 아직 명확하지 않고 지금 할 수 있는 거는 그런 오류들을 그래도 알아서 처리할 수 있는 좀 유연성을 가진 시스템을 만드는 방법밖에 없다고 그렇게 말씀하고 계십니다.
Another problem we have is that the complexity and the number of inputs means that we end up having to generate lots of test cases. We end up with a combinatorial testing problem. We have inputs coming in from the external sensors, our radar, LiDAR, number of video cameras, other sensors. We've got vehicle-to-vehicle communication. We've got GPS data coming in. We've got maps that we have to read. We've got all the information coming from the engine, the brakes, and of course we're taking input potentially from the passengers as well. If we look at the amount of information coming in, even if we did simple pairwise testing, which would be a minimum for a safety critical system, it would generate millions and millions of tests. In which case we're going to have to come up with a better way of doing pairwise or combinatorial testing, probably based on risk. We're going to have to actually come up with better ways and more formal ways of managing risk in these systems.
네, 그래서 실제적으로 조합 테스팅을 한다고 했을 때 그 시스템이 가지는 복잡성 그리고 지금 보시는 것 같이 여러 가지 인풋으로 인해서 가장 단순한 페어와이즈에 머무른다고 해도 실제적으로 몇백만 개의 테스트 케이스가 필요합니다. 그래서 이 조합 테스팅을 할 수 있는 좀 더 좋은 방법, 아마도 리스크를 기반한 방법이 될 것 같은데 그런 방법을 만들 필요가 있습니다.
And as an example of how many tests we're going, or inputs and therefore tests that we're going to have to consider, just imagine that we have one sensor, one video sensor, and it's looking at our cat again. Actually, I'm getting quite, I quite fancy a cat now. Anyway, it's looking at the cat. We're driving on a journey. There's dirt coming off the road onto our video camera. So, as we drive along on our journey, the video camera gets more and more degraded. Now, I've got 16 on there. At which point does the system report to me that it can no longer use this video camera? Is it there? Is it there? Somewhere between there and there. In which case, how many tests do I have to do to make sure the system will work with a degraded camera? Or do I say it's somewhere here and every 10 kilometres the driver has to get out and clean all the sensors to make sure they're always giving me nice results, which will not work. Oh, I said driver, of course I meant passenger, because it's an autonomous system.
네, 그래서 그림과 같이 16개의 그림이 주어졌다고 했을 때 만약에 그 흙이 쌓인 도로를 막 달려가다 보면 당연히 카메라 렌즈에 점점 뭐가 끼어서 저 품질이 낮아질 텐데 어느 시점 저 중에서 어떤 그림에서 더 이상 이제 시스템이 인식이 불가능하다고 회신을 줄 건지를 잘 판단해야 된다는 말씀을 하셨는데 그러기 위해서 어느 정도의 테스트가 필요한지에 대해서도 좀 고려를 해야 될 것 같습니다.
If someone asked me today to test one of these systems, and I'm testing the whole thing rather than small parts of it, like an individual sensor, then I think this is the best I could do, given that it's a safety-related system. This is the system I'm testing. I then go away and get a completely independently built second system that does, hopefully, exactly the same thing. Because now I'm able to use that as my test. I can compare the outputs of the two. If they differ, something's gone wrong. It might have actually gone wrong with the one the one I'm using as my test oracle, or it could be the one that's actually been built that we're going to deliver. And in fact, I might actually swap them over after some time if I decide actually this one is a better solution than this one. If it's really safety critical, add a third. Now I've got 3. The cost of building extra systems, I think, will probably be less than generating and running millions upon millions of test cases.
네, 그래서 지금 시점에서 박사님한테 누군가가 AI 시스템을 테스트해달라고 한다면은 이 그림과 같은 접근법을 사용하실 거라고 합니다. 그래서 테스트 대상이 되는 시스템과 동일한 동작을 하지만은 다르게 개발된, 별도로 개발된 다른 시스템을 붙여갖고 두 개의 결과를 비교함으로 인해서 테스트 결과의 이제 신뢰성을 높여가는 거죠. 그래서 만약에 안전이 정말 중요한 시스템이라고 한다면 한 개 말고 2개를 넣을 수도 있고, 박사님 생각에는 별도의 시스템을 개발하는 게 하나의 시스템을 가지고 무한대의 테스트를 하는 것보다는 좀 더 저렴하게 먹힐 수 있다고 생각하는 것 같습니다.
And of course, if I as a tester am coming up with this test architecture, I would hope that the people who are building safety-related AI systems are coming up with similar architectures that would actually be running in real time. So we would have multiple versions running in real time, comparing their results, and if we had 3, using a simple majority voting system in real time.
네, 그래서 뭐 실제적으로 이제 다른 AI 시스템들이 나와 있으면 그것들을 이용해서 뭐 3개를 했을 때는 그 중에서 뭐 대다수가 뭘 하느냐, 어떤 결과를 내놓느냐를 따라서 우리의 시스템을 테스트하는 방법을 사용할 거라고 합니다.
But those of you who built safety critical systems, which are based on a very similar architecture, will probably be aware that even if we build completely independent versions of systems, when we actually get those versions and compare them, we find they're not completely independent. So therefore, even though this is a nice idea, it doesn't give you as much guarantee or as much confidence as it should, because we know that we can't build completely independent systems. Even when we keep the teams completely apart, maybe in different countries, and don't even let them talk to each other, they still make the same mistakes. And where we've looked at AI systems and the adversarial perturbations, and you look at 2 completely independently built AI systems, you feed them data that causes an adversarial perturbation, and both of them are affected by the same data. So this is only a partial solution.
네. 하지만 실제적으로 이제 실제 개발을 하다 보면 뭐 아무리 2개의 팀으로 별도로 분리하고 다른 나라에 둔다고 하더라도 어느 정도 공통적인 프레임워크를 사용해서 시스템을 개발하기 때문에 보시는 그림이 이론적으로 말씀하신 것과 같이 그 정도의 자신감을 줄 수는 없고, 이 그림을 통해서 그 정도의 자신감을 줄 수 없다고 말씀을 하셨습니다.
Okay, so we can come up with different ways of doing black box testing. In a safety critical system, we're going to have to do some white box testing as well. So let's to explain the white box testing, I need to go into a bit more detail about the deep neural nets. So this is, I think, the picture I showed you before, but bigger. So our deep neural net has got, let's see, an input layer, an input node. So all of the inputs are going in here. So if you imagine, if it's an image, the different pixels are going into here. So obviously this is bigger than 3 nodes. It would be big enough for all the different pixels to go into it. And at the other end, we've got the output layer and the output nodes, which are giving us our results. In between, we have the hidden layers. We can't see these. Obviously, we just got the input and output layers. These are all hidden inside. And each node or neuron in a layer is connected to every other neuron in the next layer.
그래서 보시는 예시 그림은 왼쪽에 파란 게 인풋이고 빨간 게 아웃풋이고 중간에 있는 각각 노드들은 자기와 이렇게 그 다음에 있는 노드와 개별적으로 서로 다 연결되어 있는 그런 레이어로 구성되어 있습니다.
Okay, so we have inputs coming in, signals being passed to the next layer, and then to the next layer, and the next layer, eventually going to the output layer. So what we have is each of the nodes are connected, each of the connections has a weight, and the designer of the neural network gets to decide the weight of the framework that generates the neural network decides the weight. The neurons have a bias. So each has a bias coming out, and then the signals coming from this layer come in, the weight is applied for each of them, the bias for this one is applied, and there's a function here that generates, using that information, an activation value. So it takes in all of the inputs, it uses the weight on each of the inputs, and it uses the bias of this node to create an activation value. And this moves to the next layer. And this activation value can be positive, negative, or 0. So it would typically be 0 if we put an input in and this node thought, oh, that was really boring. Doesn't really tell me anything. That would give it a 0. If this node thought it was really interesting, the activation value coming out would be highly positive.
네, 그래서 좀 더 뭐 세분해서 보면은 각각 노드를 연결하는 연결선에는 가중치가 주어지고요. 그 가중치와 그 각 노드가 가지고 있는 편견을 가지고 이제 들어오는 정보를 처리를 해서 그 결과에 따라서 뭐 0이 될 수도 있고 포지티브가 될 수도 있고 네게티브가 될 수도 있다는 말씀을 주셨습니다.
Much better than me. So if we're doing white box testing, the hidden layers are actually not hidden from us. We can actually see the hidden layers. So we can see the values that are going across here. And we can, therefore, knowing how it works, we can come up with different coverage measures. So most basic is full neuron coverage, so every node gets covered. So that means every node or every neuron is activated and the value goes above 0. So we make the inputs interesting to every node. So we have to put in a variety of inputs till every node actually gets activated and generates a value to the next layer. This, as it says here, is similar to statement coverage. In statement coverage, every line of code is exercised. In neuron coverage, every node is activated.
네, 그래서 화이트박스 테스팅에서는 기본적으로 이제 풀 뉴런 커버리지를 위해서는 각각의 그 노드가 최소 한 번 이상 액티베이션 되게, 즉 값이 0보다 크게 될 수 있도록 인풋을 주어갖고 모든 노드를 적어도 한 번 실행하는 것이 풀 뉴런 커버리지입니다. 기존에 있었던 구문 커버리지하고 비슷한 개념입니다.
And if we can have neuron coverage, we can go a bit more sophisticated and say we'll have a threshold coverage, and that threshold coverage is only if we activate the neuron and the activation value goes above a certain threshold value. So we have to make the inputs not just a bit interesting, we have to make the inputs quite interesting, enough to get above this threshold. But of course, it's really difficult to know what we should set the threshold value to, because it would be different for every neural network. And we couldn't put it in a standard for neural networks and say threshold value has to be above this, because it would just change for every network.
네, 앞에서와 비슷한 개념인데 이번에는 그냥 양의 값으로 가는 게 아니라 어떤 특정한 역치 이상의 값이 모든 노드가 될 수 있도록 하는 게 threshold coverage인데, 실제 이 상황에서 제일 어려운 거는 저 역치 값을 어느 정도 선호를 할지를 판명하는 게 가장 어렵고, 그거에 대해서는 뭐 어떤 표준이나 그런 게 지금 현재는 없는 상황이라는 말씀을 해주셨습니다.
The next one we could do is sign coverage. And for sign coverage, we want every neuron to generate a positive activation and a negative activation, obviously on different test cases. So here, if we had test 1 going through, we've got we've got some changing. So this one here changes here. This one here has changed from positive to negative. So we would want every neuron to activate both positive and negative. So really interested and really disinterested.
그 다음에 사인 커버리지 같은 경우에는 각 노드가 이제 양의 값으로 적어도 한 번 실행이 되는 게 아니라 각 노드가 양의 값 그리고 음의 값으로 적어도 한 번씩 실행될 수 있도록 하는 게 사인 커버리지입니다.
And given that we can measure the activation values, we can have change coverage where we expect each neuron to change by a certain amount. So maybe 0.1 to 0.4. Again, deciding on a reasonable amount for it to change will be specific to each neural network. So again, this one will be difficult to set as a standard.
그리고 다음에 이제 체인지 커버리지인데, 이거는 각 노드가 적어도 어떤 특정한 범위에 거쳐서 변할 수 있는 거를, 변하는 상황을 커버하는 거를 얘기합니다. 뭐 예를 들어서 점 1에서부터 점 2까지 사이에 뭐 5가 있다 그러면 그 사이는 적어도 모든 노드가 다 변할 수 있도록 해야 되는데, 마찬가지로 여기서도 적정한 그 변화의 범위가 얼마인지를 정하는 것이 어렵고 거기에 대한 표준은 없는 상황입니다.
So all the examples I've given you so far have been by just measuring a single neuron. But actually, this technique appears to be quite effective. It will find some adversarial perturbations. And with this one, you're actually looking at two layers at a time. So what you're looking to do is change the sign of a neuron up here. So it goes positive to negative. And then look at the next layer and see if by just changing one neuron here, you can change just one neuron in the next one. So here, we've just changed this one from positive to negative. By doing that, this one, which was positive, has changed to negative, and everything else has remained the same. So we've been able to show that this neuron can independently affect this neuron, which for those of you who are into safety critical white box coverage is very similar to MCDC.
사인 커버리지는 앞에서 예제들과는 다르게 한 계층이 아니라 두 계층을 쳐다보고 있는 거고, 앞에 계층이 이제 독립적으로 뒤에 계층의 특정한 노드에 영향을 줄 수 있는 상황을 테스트를 하는 겁니다. 그래서 보시는 예제는 앞쪽에 있는 녹색이 노란색으로 변했을 때 뒤에 하위 계층에 있는 것들 중에 특정한 한 노드에 대해서만 독립적으로 영향을 미치는 상황을 보실 수 있고요. 뭐 예전에 다른 그 소프트웨어 공학서에 많이 나와 있는 MCDC하고 비슷한 개념이라고 생각하시면 될 것 같습니다.
And so we can also, so we've covered those ones through the pictures. We can also actually just look at complete layers as a whole. So we could actually look at a complete layer, look at all the activation values coming out of that complete layer, and see how that complete layer affected the next layer, or potentially affected any of the later layers. And some of the research is showing that if we can actually get one layer to affect one of the other layers that's close to it, that might be one of the reasons for causing adversarial perturbations.
네, 그래서 뭐 노드 단위로 쳐다보는 게 아니라 이제 레이어 단위로 쳐다봤을 때 하나의 레이어가 다른 레이어에 어떤 영향을 주는지를 보게 된다면 앞에서 예제로 들어줬던 그 적대적인 그런 결함들이 어디서 나오는지를 알 수 있을 것도 같다고 얘기를 하십니다.
So, looking at the test techniques we can actually use for these neural networks, the research appears to show that random testing, the traditional black box techniques that we use already, and neuron coverage, which if you remember was the most basic white box coverage, they're not very good at finding adversarial examples. In fact, the level of neuron coverage is really easy to achieve. You achieve it really quite quickly. So you don't need many test cases, so that isn't particularly surprising. If we were to look, however, at random testing, equivalence partitioning, statement branch coverage of a traditional system, they're also actually quite poor at finding defects. So maybe we're asking too much. Our traditional safety critical systems, in my opinion, are over-engineered. Maybe using a similar approach for neural networks will be okay. Maybe we have to just put them out there and see what we get. The AI people are really into these adversarial examples, which is good. It's a real problem. Needs to be fixed. We need a way of identifying them, but I am a bit worried from a testing perspective that too much effort is going into those areas, and we need a more holistic approach to saying how a suite of testing would actually work best. Because we know with traditional systems, using one approach is never any good. We have to use multiple approaches, and we have to use multiple approaches at different stages.
네, 그래서 뭐 전통적인 랜덤 테스팅이나 아니면은 그 단일 노드에 대한 커버리지는 실제 이런 적대적인 결함을 발견하는데 크게 효과가 있지는 않다고 조사가 됐는데, 기존의 예전의 시스템들을 살펴본다면은 기존의 뭐 인베디드 시스템에서 랜덤 테스팅이나 동중 분할 같은 경우에도 마찬가지로 크게 그렇게 결함을 발견하지는 않았습니다. 그래서 박사님 의견에는 이런 적대적인 결함을 발견하는 게 물론 중요하지만 지금 너무 많은 노력을 거기에다가 쏟아붓는 걸 수도 있다고 생각한다고 하십니다.
그렇죠. 질문 하나 있는데요.
네.
이렇게 테스팅 여기 얘기 파일 테스팅 하는 방법은 좋겠는데,
네.
결국 이렇게 하려면 테스트 데이터를 만들어야 될 거 아니에요.
네.
케이스 파일.
네.
그럼 어떻게 생성을 할 수 있는 건지.
So in order to achieve this, they have to do a lot of tests, and your suggestion on creating test data.
Yes, that's next.
아,
Yes.
그게 다음에 나오는.
아, 알겠습니다.
Thank you. Very good prompt for the next section. So, I think we need to use a mix, as we do for traditional system, black box and white box. As I've been saying, we need lots of test data, and therefore, if we're going to have lots of test data and we're going to run lots of tests, we need really good support. So if you wait maybe 5 slides, I'll get there.
네, 그래서 뭐 블랙박스만 아니라 화이트박스만 아니라 두 개를 적절하게 이렇게 잘 조합해서 사용해야 되고, 자동화 테스팅과 환경이 매우 필요한 거라고 하십니다.
So we need really good virtual test environments. We've had good test environments for avionics for many years. We have reasonable test environments for automotive, but the scale of testing that needs to be done for these AI systems is a level up. And the complexity of the systems means we're going to have to run lots and lots of tests. Therefore, we will need, I believe, really good virtual test environments. Before I get there, why do we need the autonomous cars in the first place? Because we could just stick with traditional systems. Well, if we have autonomous cars, we hope to reduce the number of accidents. So about 1.2 million people are killed each year worldwide in road traffic accidents. That's killed. That's not just seriously injured or injured a bit, that's killed. The people who get seriously injured, we have to treat them in hospital. Costs a lot of money. In America alone, 8 years ago they believed that they were losing more than $1 trillion worth, so that's 1,000 trillion wons worth of productivity from people who were injured in car accidents. It's an enormous amount of money. And 93% of these accidents are caused by humans. They're not caused by failures of the car, the mechanics, or failures of the systems. They're caused by people being tired, making wrong judgments, taking drugs, lots of things. Of course, if we have autonomous systems, they'll be more efficient. They will plan their routes more efficiently. We will need less cars. We will share cars because they can pick up people as they're going around. So there'll be less traffic. The environment will get better because there's less emissions. If you're someone who currently can't drive, then autonomous cars will suddenly give you the ability to go anywhere anyone else can go. So you could live in the countryside even and get somewhere. So we get better route planning. If you have to come to the office and it's a 1 hour commute, you can actually do something in that hour. If you're driving the car, all you can really do is listen to the radio or do phone calls, although in England that's illegal. I can't quite understand why playing on the phone while you're driving in Korea isn't illegal as well. The cars will be cheaper because we haven't got to deal with all the human interfaces, etc., and obviously less medical bills.
네, 그래서 앞 전 슬라이드는 이제 이런 자율 시스템을 테스트하기 위해서 가상 환경이 필요하다는 말씀을 먼저 해주셨고, 이제 이런 자율주행 자동차가 필요한 이유, 그것으로 인한 이득에 대해서 얘기를 해주셨는데, 미국에서만 한 해에 뭐 120만 명이 죽고 그 사람들 때문에 잃게 되는 생산성이 생각을 해봤는데 $1,000억 이상 된다고 합니다. 그래서 이런 자율주행 차가 가져올 장점들은 뭐 교통량이 적어지고 배출가스가 적어지고 뭐 지금 현재로서는 운전을 못하는 많은 사람들이 운전할 필요 없이 이동할 수 있는 이런 여러 가지 장점들이 있다고 합니다.
The organisation that I believe is furthest forward in this area is Waymo. Waymo are the Google driving project. They've changed their name. And Waymo have been running autonomous cars on roads since 2009. And in that 9-year period, is it 9? 8-year period, whatever, they've done 10 million miles. They've done more than anyone else on the roads. So they've got the most data, and of course that data is making their systems better. Every time the system fails, they fix the system. and then they put the system out there again, and it fails and they improve it. It's an easy mathematical reliability theory.
네, 그래서 저희 가장 앞선 업체 중에 하나인 구글의 그 자율주행 자동차 부문인 웨이모 같은 경우에는 지난 9년간 1000만 마일 이상의 그런 데이터를 누적할 수 있었습니다.
So this easy reliability theory means that if we wanted autonomous cars that were 20% better than humans, so just 20%, but that would save over 200,000 lives a year, then we would have to do, or Waymo would have to do, somebody would have to do 500 times that much driving. Now, obviously they can buy more cars, but 500 times, they would have to do 5 billion miles to get to that level of reliability. This is not possible in a reasonable time scale. Therefore, we have to come up with a better way than doing the testing on the roads.
네, 그래서 사람 운전자보다 20% 정도 더 기능이 좋은 자율주행 시스템을 위해서는 현재까지 한 거에 500배, 즉 5억 마일 정도를 해야 되는데 이런 거를 실제 도로 상황에서 하기는 현실적으로 가능하지 않습니다.
So what we will need to do is do more testing off the roads. Now, we can test on test tracks, which are safer, but again, it's very expensive, and also the testing is happening in real time. Now, we can create scenarios here much more intensely than we can create scenarios on the public roads. On a public road, we have to drive something like 150,000 kilometres before we find an accident, an interesting situation. On the test tracks, we can create interesting scenarios much quicker, but on the test track, the car is still driving at normal real-time speeds. If we move down to this level, if we're actually now running the tests on a simulator, so virtual environment, now we can run the tests as fast as we want, as fast as our processing power gives us. We've got lots of processing power. Now imagine we used all the processing power being wasted on blockchain, on cryptocurrencies, and used it here. We would run a phenomenal number of tests.
그래서 실제적으로 공용 도로에서 테스트하기가 힘드니까 테스트 트랙에서 할 수도 있는데 여기서의 문제는 마찬가지로 비용이 높고 실시간으로 이루어지기 때문에 하나의 테스트를 하기 위해서 많은 시간이 필요합니다. 그래서 뭐 프로세싱 파워가 있는 한 최대한 빨리 돌릴 수 있는 가상 환경을 만들어서 테스트를 진행하게 되면 훨씬 빨리 할 수 있다는 얘기를 해주셨는데 이제 크립토커런시에 들어가는 가상화폐에 들어가는 모든 파워를 갖다가 하면은 상당히 많은 테스트를 할 수 있다고 말씀을 해주셨습니다.
So of course, if we're down here, we have absolute control of our tests, and we have absolute observability. We can see everything, and we can control everything. Up here and here, there might be things causing problems or causing it to work even that we don't know about. There could be some data coming into the system and we're not clear what data it is that the AI is actually using. And this is not to scale, obviously. Here's a quote from someone saying 99.99 needs to be here. I don't know the numbers. I do know that if I drew this to scale, as I believed it should be, you wouldn't be able to see these two, because they would be tiny, tiny bit at the top of this pyramid. Most of our testing has to be down here.
네, 그래서 가상 환경에서 하면은 장점으로는 이제 모든 데이터가 어떻게 흘러가는지 이런 걸 볼 수 있다라는 장점도 있고, 실제적으로 이 표 같은 경우에는 그냥 보여드리기 위해서 표가 이렇게 그려진 거지, 실제 필요한 걸로 그리게 된다면 이제 제일 마지막에 밑에 있는 가상환경이 뭐 그림의 대부분을 차지하고 있을 겁니다.
So I've talked about the benefits. Of course, there are some disadvantages as well. And the main disadvantage is that if we go this route, which I think we have to do, then we have to build really good simulators. We have to take simulator technology beyond where it is for avionics. But we should be able to do that. I don't think that is particularly difficult. Avionics simulator technology has been stuck for about 20 years. We can do this if we actually recognise the benefits that we're going to get out of it. So we need good quality simulators, move them forward from where they are now.
네, 그래서 뭐 장점은 앞에서 설명을 드렸는데 단점으로는 당연히 이런 시뮬레이터 환경을 현실에 충실하게 만들기 위해서는 많은 노력이 필요한데 현재 그 항공 관련된 시뮬레이터들의 수준을 훨씬 뛰어넘어야 되고 당연히 실현 가능할 거라고 생각하고 계신다고 합니다.
So I'm not saying that we don't need to actually test on the roads or on the test tracks, but what I think is we should use all the information we can get from those tests. Whenever we find anything interesting up there on the roads, on the test tracks, we then feed that down here into our virtual environment and run millions upon millions of tests around those scenarios.
실제 도로에서 이제 관심을 끌만한 케이스나 데이터가 발생하게 되면은 그거를 이제 가상 환경에다가 넣어서 그 테스트 데이터를 가지고 이제 뭐 수백만 개의 테스트를 실행할 필요가 있다고 얘기하십니다.
And where we actually find critical scenarios that cause the systems change, so we've actually caused a failure, we've caused the system to be changed by the developers, then once we've actually done that, we then feed those up to the test tracks and the public roads and make sure that those critical scenarios are really carefully tested in the real world.
네, 그래서 밑에 가상 환경에서 뭐 치명적인 시나리오 같은 경우에는 가상 환경에서 머무르는 게 아니라 결국에는 위쪽으로 올려갖고 이제 공연도로에서도 매우 세심하게 테스트할 필요가 있다고 합니다.
So we need to create lots of test scenarios, and in the next section I'll explain more about where I think those test scenarios should come from.
그래서 많은 시나리오가 필요하고 다음 섹션에서 그런 시나리오들이 어디로부터 올지에 대해서 의견을 말씀해 주시기 바랍니다.
But once we have scenarios, driving scenarios, then we can actually use AI, or maybe even use old technology like fuzzing and mutation, to take those scenarios and generate lots and lots of instantiations of that scenario based on what we know are valid changes to the attributes.
그래서 좋은 시나리오를 생성하게 되면은 이제 AI나 아니면 기존의 예전의 전통적인 방법들을 활용해서 그 시나리오로부터 여러 가지 파생되는 기타 시나리오를 생성할 수 있습니다.
So, as you probably gathered from what I've said already, I believe we need regulation, and that would require a government to set up regulators. I haven't got time to talk about how this might be done across international boundaries, because obviously that needs to happen, because if Hyundai, Kia are making cars in Korea and exporting them to every other part of the world, the regulations have to apply worldwide as well. But we set up a regulator, and that regulator can work with a safety standard, presumably generated by a standards body, and then the safety standard is used in a test lab, and that would check whether our autonomous car is actually safe enough.
네, 그래서 규제가 필요하고 규제가 뭐 국제적으로는 어떻게 형성되는지에 대해서는 뭐 시간 관계상 건너뛰신다고 하는데 일단 규제가 필요한 상황이고 그 규제로부터 이제 안전 관련된 표준이 생성이 되면 그 표준을 가지고 테스트랩에서 자율주행 자동차를 확인함으로써 이게 충분히 안전한지를 검증할 수 있다고 말씀하셨습니다.
One of the questions is, if the regulator says you have to build your car and it has to meet this safety standard, therefore it has to pass all these tests, the question is, do we trust the OEMs to do the testing? Well, as an owner of a Volkswagen, I'm not sure I trust OEMs to do the testing. And the problem is that the amount of money to be made here in autonomous vehicles is much more than the money to be made through fixing or cheating on a simple emissions test.
네, 그래서 저런 규제를 하는 표준이 있는 경우에 여기서 가지는 의문 중에 하나는 이제 실제적으로 그런 테스트를 OEM 자체적으로 할지 아니면 뭐 외부기관이 할지 그런 거에 대해서 생각이 필요하다는 말씀을 해주셨고 복스바겐을 가지고 있기 때문에 OEM이 하는 거에 대해서는 좀 약간 부정적이라는 말씀을 해주셨습니다.
So where do we actually, we have to generate the rules, and these rules come from would be created from a number of different inputs. Basically, up here, these are the rules of the road. These are the laws that are currently applied to driving in Korea or UK or US or whatever. Obviously, we've got other factors that we have to consider as well, but largely it's the rules that we already have. Now, those rules have a problem in as much as every country has their own set of rules. I don't believe it's going to be sensible to have a different set of rules for autonomous systems for Korea and for China. It wouldn't be cost effective.
네, 저는 규칙을 만들 때 뭐 이제 인풋을 받는 거는 여러 가지가 있는데 기존의 뭐 법적인 저런 law들이 있겠죠. 그리고 실제적으로 이런 것들에 대한 저 규칙을 만들 때 한국 따로 중국 따로 이렇게 따로따로 만드는 거는 효율적이지 않다고 생각한다고 하십니다.
So these safety rules would be generated by a standards body, a set of experts presumably, and this is our autonomous system. Safety rules get applied and we check if the system can cope with the rules.
그리고 저런 규칙들은 이제 아무래도 뭐 국제 표준기구나 이런 데서 저런 규칙들을 만들게 되면은 당연히 시스템에 적용을 해서 시스템이 거기에 합당한지 확인하게 됩니다.
The rules shouldn't be complicated. If they're complicated, the public won't trust them. So the rules have to be simple. So this is my example of a particular rule. This is simple. Hopefully it's a simple rule. And basically, it's if you're following another vehicle, how close can you get to that other vehicle? You can imagine that the rule could say that there is a virtual envelope around every vehicle on the road. And that envelope would change shape depending on the speed of the car and the manoeuvres it was doing, but that's easy. We can do maths. And then the rule would say this vehicle, the eco vehicle, the one we're testing, cannot go into this area. If it goes into this area, it's failed the test. Our regulator says, sorry, that vehicle can't go on the road because it's unsafe.
네, 그래서 화면을 보시고 계시는 예제는 이제 각 차별로 안전거리를 어떻게 유지할지, 어느 정도를 유지할지에 대한 예제를 들어주셨고요. 규칙에서 이제 각 차별로 속도에 따라서 어느 정도의 거리를 유지할지를 정하고, 규제하는 기관에서 거기에 따라서 이제 각 차를 테스트하게 될 경우, 뭐 저거를 거기에 따라서 테스트를 할 수 있다고 말씀해 주셨습니다.
Okay, so this is an example of a function. This vehicle is following that vehicle, and the safety rules should cover the functionality. They also have to cover the context in which the rules apply, because the rules will change if we're in the rain, or if we're in fog, or if it's a clear day. Because if it's in the rain and the vehicle brakes, it's going to take longer to stop. If it's in the fog, the video cameras on the front of the car will not be able to see the car in front as easily. Now, several agencies and research projects have already looked into this. So, a lot of this work is already done.
네, 그래서 이런 규칙들을 만들 때는 당연히 뭐 해당 기능뿐만 아니라 해당 기능이 적용되는 상황에 대해서도 살펴봐야 된다는 얘기를 해주셨고, 지금 현재 이런 규정들을 만들기 위해서 노력하는 단체들이 여러 개가 있으며 대부분의 작업은 이미 끝나 있는 상태입니다.
And yeah, this is the US government or its agency has identified 28 functions. The one that we were just looking at was number 7, perform car following. Waymo, which we were talking about earlier, who I think are probably a bit ahead of the game, have actually taken that 28 and have added another 19.
그래서 앞장에서 보셨던 게 미국 정부 기관 에이전시에서 정의한 28개 규칙들이고요. 뒷장에서 보시는 거는 뭐 가장 앞서 있는 웨이모에서 그 정부 규제에 추가로 더한 이런 규정들입니다.
So lots of the functions are already defined, and as for the context, we need to know what road type it is. Is it a small road? Is it an expressway? Whatever. Is it in the city, mountain, desert? What speed will vehicles be doing? And the environmental conditions. And the good thing again, research has already done lots of this work for us. So we could actually just go away and pick up a complete set of these already.
그래서 기능에 영향을 주는 상황에 대해서는 뭐 지리적인 위치나 속도, 제한 속도나 여러 가지가 있을 수 있는데 마찬가지로 이런 상황에 대한 조사도 이미 상당 부분 많이 되어 있다고 말씀하십니다.
So going back to the pyramid, these tests are going to be run virtually. They're going to be run in the virtual test environment, which means we're going to need well-defined test environments. The core set of tests will sit here. These will be shared. The OEMs will see all these tests, so they'll know how their vehicles are going to be tested. However, they'll be parameterized. There were only 47, I think, examples I showed you, but of course for each of those 47 there are lots of variables that we could change. And if we were testing, each of those 47 might have, in our virtual test environment, we could run 1 million tests, because it's a virtual test environment. We can set some AI running to change the parameters within reasonable limits and run them in virtual scenarios. We would also have some private ones. By private I mean these ones we don't share with the OEMs. Because there is the danger, of course, if we share everything with the OEMs, they just write systems to match the tests. And if our tests aren't completely comprehensive, that is dangerous. In effect, that would mean we as the regulator would be setting the requirements for these cars. That wouldn't work, or it would be dangerous. So we would also have some private ones, not seen by the OEMs, to make sure that they didn't just try and fit the test data.
그래서 만약에 저희가 규제하는 입장이라고 생각을 해봤을 때는 이제 OEM들과 이제 공유하는 그런 테스트 세트들이 있을 거고, 테스트 세트는 앞에서 뭐 47개인가 보셨는데 각각 뭐 바꿔가면서 할 수 있는 변수가 많기 때문에 어느 정도 이렇게 통제된 그 범위 내에서 이루어져야 되고, 만약에 우리가 규제하는 입장에서 전부 다를 OEM한테 알려줄 경우 거기에 딱 맞는 기능만 구현해갖고 올 거기 때문에 이제 공유하지 않는 프라이빗한 규제 테스트 시나리오들도 별도로 두어야 된다는 말씀을 하셨습니다.
So if we have the systems out there running and there's an accident and we think the accident is caused by the autonomous system, one of the regulations would be that the autonomous systems had to automatically report incidents back. In fact, the software testing working group in ISO are now working on incident management standards to help define how that information could be collected. So the autonomous system would automatically send information back to the vendor. It would also have to send it back to the regulator. And the regulator would then look at the data and say, oh, actually, and this would require us to have intelligent people, scientists or engineers working at this level, not just bureaucrats. They would have to analyse that data and say, actually, that data tells us that there is a dangerous scenario that could actually affect all different types of cars, in which case they will send a message out to all vendors saying, new dangerous scenario that wasn't included in the test set that we gave, that we certified your system to, please take care of it.
네, 그래서 어떤 사고가 발생하게 될 경우에는 사고에 관련된 데이터가 벤더뿐만 아니라 이제 규제하는 기관까지도 가게 되고, 규제하는 기관에서는 데이터를 잘 살펴봐서 만약에 전체적으로 뭐 수정이 필요한 상황이라면은 모든 벤더들한테 해당 정보를 이제 배포하는 상황이 발생합니다.
And this data, and it says accident and attack data because if we're looking at safety critical systems that are connected to each other and connected to the internet, etc., they can easily be attacked as well. And this data is going to be shared by many different agencies. Some of them are going to use it, some of them are going to supply it.
네, 그래서 뭐 사고뿐만 아니라 이제 이런 시스템에 대한 공격에 관련된 데이터는 지금 그림에서 보시는 것과 같이 여러 사람들 간에 공유가 되게 됩니다.
So, as the regulator identifies bits that are missing from their tests, the original tests, they will have to generate safety updates, and those safety updates will go to the vendor who will ideally do over-the-air improvements to their systems.
네, 그래서 그런 보안 관련된 업데이트가 벤더한테 넘어가면 벤더는 이상적인 상황에서는 OTA를 통해서 각각의 차로 해당 정보를 배포하게 됩니다.
Okay, my conclusions. As I've said many times, the probabilistic testing means you have to generate more tests. We already know that for traditional safety critical systems, we spend 80% of our budget on the testing and 20% of our budget on the development. So, when we come to test these autonomous systems, we should not be surprised that the testing costs are far higher than the build costs. The industry needs to understand this. I don't think they understand this now. I think their belief is that if they spend lots of time developing, that the testing will just be an easy bit at the end. Especially the people who have come into the market, like Uber, Tesla, who haven't got the background in automotive engineering.
네, 그래서 말씀드린 바와 같이 확률적인 테스팅을 위해서는 테스트가 굉장히 많이 필요하고 예전에 전통적인 시스템을 봤을 때 전체 예산 중에 80%가 테스팅에 투입되기 때문에 이런 시스템을 개발할 때는 당연히 테스팅에 많은 비용이 들어갈 거라고 예상하고 들어올 필요가 있다고 말씀하셨습니다.
So, we need many tests because they're probabilistic, they're probably the most complex systems that we've seen, and they're going to be highly critical. They'll kill people if they go wrong. And we're going to need really sophisticated virtual test environments. It's a really big area that we as an industry need to get into. The test techniques for testing these deep neural networks are really in their infancy. The test techniques have been invented by people in universities who are building systems who have gotten little or no background in testing. They need help. They need support from the real-world testers. So we need to do empirical studies. When they come up with a new technique for testing them, well, don't just accept that new technique because it works on the system they just built. That's not good science. We need empirical studies. If someone comes up with a technique and they say, this is an effective technique, get independent research. Get other people to actually redo the tests on different systems. And we shouldn't just concentrate on the adversarial examples. They need to be handled, but there'll be other problems that we haven't identified. The ones we haven't identified are going to be more dangerous. At least we know adversarial examples exist, so we can build something to cope with it.
네, 그래서 오토모티브 시스템을 테스트하기 위해서는 많은 수의 테스트 케이스가 필요하고 좋은 가상 환경이 필요하고 그리고 이와 관련된 테스트 기법들은 지금 막 나타나기 시작하는 단계이기 때문에 누가 어떤 기법을 발표한다고 해서 그거를 무조건 믿을 게 아니라 그것을 검증하기 위한 여러 가지 리서치하고 활동들이 필요하고요. 그 다음에 저런 적대적인 결함에 너무 집중하지 말고 저것들을 어느 정도 처리할 수 있는 유연한 시스템을 만들고 집중해야 되는 다른 부분에 좀 집중을 할 필요가 있다는 말씀을 하셨습니다.
And we're not very good at this at the moment, so until we reach some level of maturity, I think we need to use a safety net. And if we're going to put autonomous systems out into the real world, then we need to actually build in some determinism. So, fine, have an autonomous system, but don't let it control everything on its own. Have some monitor function, perhaps based on those safety rules and the safety envelopes that says, because that's quite easy to check. So this monitor function checks, if you cross the boundary of that safety envelope, then I'm going to take over and I'm going to take the car or the drone or the ship, whatever, to safety. Until we know that we can build these safely, I think this sort of architecture is absolutely necessary.
그래서 현재까지는 저런 자율 시스템의 안전을 확신할 수 없기 때문에 지금 시점에서는 저 자율 시스템을 어느 정도 보완할 수 있는 안전망이 꼭 필요하다는 생각을 피력하셨습니다. 그래서 앞서 말씀드렸던 규제 등을 기반으로 해서 저 자율 시스템이 뭔가 실수를 했을 때 그거를 커버할 수 있는 모니터 시스템이나 기타 안전망이 필요하다는 말씀을 해주셨습니다.
아까 테스트 쪽에 한 80%의 비용이 들어가고 20% 정도가 개발 비용이 있다고 발표해 주셨는데요.
네.
그 80%의 테스팅 비용이 테스팅 도구인지 아니면 환경인지 아니면 테스팅을 하는 사람 그 그런 여러 가지 테스팅 비용의 부류가 여러 가지가 있는데요.
네.
어떤 쪽에 이제 많은 비중이 그 80%가 더 들어가는지 혹시 거기에 인증 비용도 포함되는지
네.
설명해 주셨습니다.
You talked about the 80% that goes into testing on embedded systems. Could you break down that 80%? Like how much you put into people, how much you put into school? And does the 80% cover certification costs?
Yes, sorry, I haven't got the breakdown of the 80%, but it covers all quality assurance and testing costs. Certification, I'm not sure.
그래서 80%가 정확하게 어느 정도 비율로 이렇게 구성됐는지는 지금 자료가 없으신데 거기에는 당연히 QC뿐만 아니라 QA 활동까지 포함해서 80%가 된다고 이해하시면 될 것 같습니다. 네.
지금 말씀하시는 거 들어보면 자율주행차 나오려면 아주 한참 멀었을 것 같은데
네.
지금 생각에 어느 정도 시기가 되면 레벨 4 정도 되는 자율주행차가 나올 수 있는 분위기.
So your views on when we will actually get automotive, when do you think we will get actual cars?
Okay, well, I have a Volkswagen, as I told you, and it's 11 years old, and in Europe, they've just changed the emission tests, and they tell me that my car after next year is. So I have to decide: do I want another car, or to wait for this? I'm definitely going to buy another car, and I'll expect to be using it for 8 to 10 years.
뭐 정확하게 예측하실 수는 없는데 지금 11년 된 복수하겐을 바꿀 때 다음에 사는 차는 적어도 한 8, 9, 10년 정도는 사용해야지 저런 자동차가 등장하지 않을까라고 생각하신다고 합니다. 네.
오늘 상당히 좋은 말씀 많이 들었고요.
네.
같이 지식을 공유하는 의미에서
네.
하나 좀 여쭤볼게요.
네.
특히 유럽 사람들, 뭐 미국 사람들은 조금 이제 괜찮은데 유럽 사람들은 이 한국 사람들을 보면 다 똑같이 보인다는 거예요. 누가 누구인지 구분이 잘 안 돼요. 그 다음에 뭐 우리나라 사람도 마찬가지죠. 우리나라 사람도 유럽에 가면 이 프랑스 사람인지 독일 사람인지 뭐 스위스 사람인지 잘 몰라요. 그냥 하얗고 뭐 뾰족하고 뭐 이런 것만 보이는 거죠. 근데 이제 그 오래 살다 보면 확실히 구분을 하거든요. 아, 이건 프랑스 사람이다, 이건 독일 사람이다. 그 다음에 이제 서양 사람도 한국에 와서 이제 오래 살면, 특히 어렸을 때부터 살면 여러 가지 그 차이점 구별을 많이 해요. 형제간 구별이든지. 그래서 그런 현상은 뇌의 이제 인지 기능에 기반한 건데, 그걸 잘 활용하면, 그 원리를 잘 활용하면, 인공지능, 아까 여기 뭐, 구분, 변별을 하는 거, 이런 것을 더, 정도를 높일 수 있지 않을까. 빠르고도, 빠르고, 정도도 높고. 혹시 그런 분야에서 학술 문헌을 보신 적이 있는지,
그러니까 이제 그 사람들이 뭔가 이렇게 사물을 쳐다볼 때 그 사물에 대해서 이렇게 구별하는 그런 거에 대한
뭐 간단한 뭐 모양이 아까 여기 이제 그 수완도 뭐 제대로 보면 못 온다는 거예요. 그런데 사람은 뭐 어느 나라가 확실하거든요. 그러니까 아까 여기 이제 그걸 어떻게 그러면 해석을 할 것인가 그런 걸 방법을 내놓는데 그 방법 말고 다른 방법이 없나?
You showed the example of the 15 characters, the one that was recognized as a dog, right?
Yes.
Are there any studies or any papers that you know that do research on how people can distinguish between how people actually distinguish between one and the other.
There are many, many papers on adversarial examples or perturbations. So there are many papers, and I have many here. There is no way that a human can spot the difference between one and the other. That's the real problem. From our perspective, if we were doing black box testing, we just cannot see the difference. In those pictures, I changed a few pixels. You can't see the difference. I can't see it on a high definition screen. It's impossible to see.
But are there papers on actually how human beings differentiate between, A and B, and how people see?
So I don't know. You mean just normal vision?
Yes.
I'm sure there must be. That's not my area.
Do you know of any other ways we could differentiate, tell the system to differentiate between two different objects? No.
No, that's.
Okay. 특별히 지금 박사님께서 이렇게 사람이 어떻게 사물을 구별하는지에 대해서 그런 논문이나 그런 페이퍼에 대해서는 아시는 게 지금 전문 분야가 아니시다 보니까 거기에 대해서는 아시는 게 없다고 보고, 실제적으로 이제 지금 여쭤보신 것 중에서 시스템이 어떻게 이렇게 구별하는지에 대한 논문에 관련돼서는 지금 자료를 따로 갖고 계시는 게 있으신 것 같으니까 그건 제가 끝나고 나서 좀 다시 한번 여쭤보도록 하겠습니다. 네.
주로 이제 지금 말씀해주신 어떤 룰이라든가 스탠다드나 이런 자동차에 관련해서 말씀해 주셨는데요.
네.
나사나 이제 FAA 같은 경우는 예전부터 이런 자율 시스템에 대한 테스팅에 관한 연구도 좀 하는 걸로 알고 있는데, 비슷한 예를 들면 상태인지, 아니면 그쪽에서 뭔가 좀 어떤 레귤레이션이나 룰이나 이런 게 더 좀 확립이 되다 보는지 트렌드를 좀 알 수 있을지.
Are you familiar with the progress from maybe NASA or any other organization related to automotive systems?
Yeah, NASA wouldn't do anything with automotive systems.
No, not automotive.
Oh, autonomous
Yes,
systems. So ISO are working in this area. ISO now have a completely new committee that just is looking at artificial intelligence, and one of the parts of that is looking at machine learning. The software and systems engineering part of ISO is looking at autonomous systems because I'm leading that project. From the testing perspective, the ISO software testing working group is actually looking at new standards on test environments and test scenarios to support potential virtual environments for things like automotive, drones, etc. I know that many other organisations are. I believe that NATO have a big project that's looking at autonomous systems, and the European Union have a project. Everyone seems to have projects on autonomous systems at the moment.
네, ISO에서도 지금 이쪽 자율 시스템과 관련해서 워킹 그룹을 새로 만들고 있고, 그것을 통해서 이제 여기를 좀 들여다보기 시작했고, 네이토뿐만 아니라 유럽 쪽이나 다른 쪽에서도 많은 다수의 프로젝트를 진행하는 걸로 알고 계시다고 합니다. 네.
Yeah, my question is regarding the white box testing of neural networks, and as per my understanding is that we try to check the coverage of the test cases, that all the neurons or the layers are activated. Is that was it connected to the explainability of what neural network is doing? Because just from looking at it, it seems that if a neural network can explain what certain features or what characteristics is trying to classify the picture or video, or maybe we can test it more comprehensively. For instance, in the case of the tags that we showed, if we find out that the sky is one of the features that is being used as classification, then we can test for that. So is the white box testing and explainability are connected, or they are separate things? And if they are separate things, are we looking at the explainability as a testing solution as well?
Right. Sorry. So I think it's the three things.
Yes.
The first thing was yes. That was the white box testing. Are we actually looking?
The coverage of the whole test,
Yes.
Test cases. Are we having the coverage completely so that all the neurons are being activated? And is that the?
That would be a minimum coverage, but
Is that the reason for white box testing, so that we check the coverage of the test cases?
it's not so much to check. Well,
It's more.
that's partially, but some of the techniques that I showed you are there to try and unearth adversarial examples as well. So the white box testing has multiple different reasons, and we don't know. We don't know how good the levels of coverage are. We need to do some research, because I showed you 5, I think, but to be honest, you can sit there and make up more levels of coverage as you're going along, and no one knows which is better, because they come up with a level of coverage, they use it against their system, and they don't. It's very limiting.
Looking at the neurons and their activation, it's not concerned with the test cases that we are using. Are they two different?
Well, obviously it's concerned with the test cases, because the test cases are being generated to achieve the level of coverage. As far as the explainability is concerned, I think potentially there are some of the neural networks now, you can actually look to see how images change as they go through the neural network. So potentially, if it was an image, you could imagine, you could look at it and say, because you said about the tanks, and maybe you could see that the sky was getting too much notice by the system. But when you actually look at the pictures as you go through, they look really weird as they're going through. So you'd have to have quite a good imagination. And that would only work for image processing. Because if we're doing the decision part of the framework, we haven't got a way to visualize that. So that would be a completely new research area. And as for being able to explain what they're doing, I'm not sure that many of the frameworks are sophisticated enough to do that. Maybe for safety related, maybe that will have to be something that is built into them. So we say that if we're going to certify this framework as good enough for safety critical, safety related, then it has to have that ability.
I'm just saying, if we have explainability here, then probably the testing can be much more intuitive and maybe easier as well.
The white box testing, yes. The black box testing, obviously, it's just end to end, so it doesn't really matter what it is we're testing in that respect. But for the white box, absolutely.
Good point.
네.
이제 미국에서는 아까 자율주행 기능에 28가지 정도 시험을 한다고 했고,
네.
외국에서는 추가적으로 47가지를 한다고 했었는데,
네.
그 시험을 할 때 이제 화이트박스 테스트하고 이제 블랙박스 테스팅 같이 하실 것 같은데,
네.
블랙박스 테스팅 같은 경우에는 정확하게 1점 대비 출력이 나오니까 명확하게 맞다 틀리다를 내가 이제 이거는 옳다 틀리다를 규정을 지을 수 있을 것 같은데
네.
화이트 박스 테스팅 같은 경우에는 어떻게 보면 커버리지를 얼마 차지하느냐 이걸 이제 보신다고 보시는 거예요.
네.
그럼 그 커버리지를 얼마까지 해야 이게 괜찮다, 정당하다 이런 거에 대한 혹시 연구가 진행되고 있는지.
The 27 regulatory rules that you explained, from a black box perspective, you would have expected outcomes, so we get how you would verify that. But from a white box perspective, are there any specific coverage criteria for each, or?
Absolutely not. No, that is. We, as an industry, we don't know how good the white box coverage measures are, so no one is brave enough to say you have to have this level of coverage, because even though 30 years ago when we created, 30, 40, whatever years ago, when we created the safety critical standards for traditional systems, no one knew how good the white box was then, but intuitively we thought they were okay, and we used them, and as I said earlier, I think we've over-engineered our systems because of that mistake 30 or 40 years ago. This time we should, if we're going to, when we create a standard that includes white box coverage, we should know from research already how good the techniques are and how valid they are. Because we've made that mistake once, we shouldn't make it again. But yeah, good question.
Just meaning is try to estimate the coverage, not to define it is correct or not.
I think if I was building a system and testing a system and I measured and if I found every neuron wasn't covered, that would make me extremely worried. But actually setting it in a standard would again make me worried if I did that without knowing that it was worthwhile. Because actually the neuron coverage sounds like a really good idea, but my understanding is that 2 or 3 tests will generate neuron coverage on a relatively complex neural network. So having a standard that just tells me to do 2 or 3 tests it's giving me false confidence.
네, 저희 시간 관계상 질문은 여기까지 하고 혹시 끝나고 나서 요 앞에 계실 테니까 추가적인 질문 있으시면 요 앞쪽에서 해주시면 감사하겠습니다.